All right, welcome linear algebra students. So in this video, we are going to continue our exploration of matrices, diagonal matrices, and similar matrices, and see why, given a matrix, it's going to be really nice to try and find a similar matrix which is diagonal that will help us simplify calculations considerably. And so let's kind of illustrate what is particularly nice about diagonal matrices. So let's imagine we had a 3 by 3 diagonal matrix D with the entries 2, 3, and -5 on the main diagonal and zeros everywhere off of the main diagonal. So what it means for a matrix to be diagonal is that all of the entries off of the main diagonal must be 0. On the main diagonal, we could have 0, we could have non-zero terms, but off the diagonal, we must have 0 terms. So here's a matrix D, and we know quite a bit about this matrix just by looking at it without doing any calculations. So one thing that we know is that for diagonal matrices, the determinant is equal to the product of the entries on the main diagonal. This is actually true for triangular matrices, and a diagonal matrix is a special case of a triangular matrix. So I know that the determinant of this matrix is 2 times 3 times 5, which gives us 30. And right away, we can see that D is an invertible matrix because its determinant is 30, which is not equal to 0. From a diagonal matrix such as this one, we could identify that the eigenvalues are the entries along the main diagonal, which are 2, 3, and 5. And again, this is a property of triangular matrices that the eigenvalues are the entries on the main diagonal. And so certainly that's going to apply to diagonal matrices. So again, we could identify based on these eigenvalues that D is invertible because it does not have 0 as an eigenvalue. And another nice property of diagonal matrices, which is not true for triangular matrices, is that it is really, really nice to exponentiate these matrices. So if I want to take D and multiply it times itself k times, well, matrix multiplication, that gets quite complicated. So doing k different matrix multiplications is going to take quite some time. But if you have a diagonal matrix, then multiplying D times itself k times, which we write as D to the kth power. So here k is some positive integer. That's going to equal just the power, the kth power of the diagonal entries. So it's going to be 2 to the kth power, 3 to the kth power, 5 to the kth power, and zeros for all of the entries off of the main diagonal. So rather than multiply k different matrices, all we have to do is 3 different operations, which is take 2 and raise it to the kth power, take 3, raise it to the kth power, 5 to the kth power, and that is considerably less calculations than calculating this matrix product. Okay, so let's take a look at an example that we have previously worked with, and that is if I have a matrix A, we are calling this matrix which has the first column minus 13, 12, and 24. The second column is minus 8, 7, and 16. And the third column is minus 4, 4, and 7. And we've shown that this matrix A is similar to matrix B, which in this example is a diagonal matrix where the diagonal entries are minus 1, 3, and minus 1, and all of the off-diagonal entries are 0. And these two matrices are similar because there exists a matrix P that we have over here. And in this case, the matrix P is 1, minus 2, 1. The second column is 1, minus 1, minus 2. And the third column is 2, minus 3, 0. And we can find the inverse of this matrix, and that we have on the left side of matrix A. And so multiplying P inverse times A times P gives us this diagonal matrix B back. So that's why we say matrix A and B are diagonal. So one thing that's really nice is we know that similar matrices have the same eigenvalues. So matrix B has eigenvalues of minus 1 and 3, minus 1 having multiplicity 2. So we know that matrix A also has eigenvalues -1 and 3, with the eigenvalue -1 having multiplicity 2. We'll also be able to apply this nice property about exponentiating diagonal matrices to a matrix which we know is similar to a diagonal matrix. So let's see how that might work. Let's say, for example, I want to multiply A times itself k times, where k is some positive integer. And here A is a 3 by 3 matrix where none of the entries are 0. So multiplying A by itself, that involves a bunch of calculations, and doing this over and over and over again is actually quite a lot of work. But let's use the fact that we know A is similar to diagonal matrix B. So I've got that A is equal, since we know that P inverse AP is equal to B, this tells me that A is equal to P times B times P inverse. And this transformation we can see above, that if I take this identity P inverse AP is equal to B and multiply both sides of that equation on the left by P and on the right by P inverse, then the left side of the equation we get identity times A times the identity, which just gives us A. And on the right side we have P times B times P inverse. So we're going to plug in this expression P, B, P inverse for A, and we're going to multiply this by itself k times. And you might be thinking that I'm crazy because this is already pretty complicated to calculate, and now we're adding in even more matrices. This seems like we're making life worse. But look at what happens. Inside these products, we have a bunch of P inverse times P's. So I could write this as P times B, and then times P inverse P, times B, times P inverse P, times B, etc., k different times. But we still have this initial P, which doesn't have a P inverse it's being multiplied by, and this last P inverse on the right. So this extremely complicated product actually simplifies down to, we have this first P over here, and then these P inverse P's, they're all going to be the identity matrix. So we're going to have B times the identity times B times the identity, etc., times the identity times B. We do this k times the identity matrices. When we multiply a matrix by the identity, it doesn't do anything. So what we're going to get is B times itself k times. And then we have this P inverse on the right. So finding A to the kth power, which involves multiplying k different matrices, we can rewrite this as a product of 3 matrices, P, B to the kth power. So this is itself, k matrix products, but because B is diagonal, we can calculate this very quickly, and then we have P inverse on the right. So this gives us, therefore, that A to the k is going to equal matrix P, which we have over here, times B to the kth power, which we have in the middle. Again, here we don't need to multiply bk times, we just need to raise each of the diagonal entries to the kth power. And this is true only because B is diagonal. And then we multiply by P inverse on the right. So this matrix of this product of k different matrices simplifies down to just a product of 3 matrices, one of which is diagonal. So the point here in this introduction to working with diagonal matrices is that they're super nice diagonal matrices where it's really easy to calculate determinants, to find eigenvalues, to exponentiate those matrices.